So the next step of defining our model is going to be defining the model that we apply to our morphological character alignment. Now, as we stated in the introduction, we are going to use the MK model for the morphological character data. This is a generalization of the Jukes-Cantor model, so we can create the MK rate matrix from a Jukes-Cantor matrix. And this is what we're going to do here. Now, the Jukes-Cantor model doesn't have any parameters, so this is simply a constant node that we call QMorpho. And it's defined from a Jukes-Cantor matrix, but with only two states, because our morphological character alignment is coded purely with two character states. Now, we will also assume that we have some rate heterogeneity between the character states, and we're going to model this rate variation using a gamma distribution. Now, the first step for this is to define the shape parameter of the gamma distribution. We're going to estimate the shape parameter, so we create it as a stochastic node with a prior distribution that is an exponential distribution with a rate of 1, as shown here. Then we also need to define the number of categories that we're going to use for our gamma distribution, and here we choose to use 4. So then we can finally create the site rates, which are deterministic. They're completely given by the shape parameter on one hand and the number of categories that we just defined and that we're going to fix here. So this is created using the function discretize gamma distribution. And then finally, the last step is, of course, we just created a stochastic node, so that means we need a move for that node, and this is what we do here with a simple scaling move on the shape parameter. Finally, the morphological evolution model needs also a clock model. And for simplicity, we're just going to use a strict morphological clock, where all the branches of the tree evolve according to the same rate. And so this clock rate is what we define here. Again, we want to estimate it, so we set it as a stochastic node with a prior distribution. And again, this is a stochastic node, so we need to apply a move to it. Now that we have all the components of our morphological evolution model, we are getting ready to assemble them within a distribution. And so with that distribution is going to be created by creating a stochastic node that we will call phi-morpho, and this is going to correspond to the outcome of the morphological evolution process. So the morphological alignment in a nutshell. And so this is given by the phylo-CTMC distribution, which uses a number of parameters. The tree, which we have defined earlier according to the FBD prior distribution, then the site rates, which we defined above, the branch rates, which are all the same since we're using a strict morphological clock, the instantaneous rate matrix, again, which we defined above. We're using a standard type of data because this is morphological data. And then we're going to set the coding variable to account for the fact that we only recorded characters in our data matrix that were variable, and we didn't record any constant characters. So this is to correct for ascertainment bias. Now, of course, we just set phi-morpho as a stochastic node, but in reality, we know what the outcome of the morphological evolution process is because we have data on that. And so the way we are going to set that in our analysis is by using this command, which will constrain the outcome of the phylo-CTMC process to correspond to the morpho object, which of course is our morphological alignment that we loaded originally. So this is our data. So now we've created all the components of our model, and so now we can now assemble it into one variable that will make it easier to set up the MCMC run. Now the way this is done in RefBase is that assuming all the elements of your model are connected, you can just create the full model by starting from one element. Here we've chosen to start from the FBD tree, and then it's just going to run through all the connections and assemble all the objects that are part of the model together. Because of course the FBD tree is connected on the one hand to the FBD distribution, which is itself connected to all of its parameters, and on the other hand the FBD tree is also connected to the phylo-CTMC, which we just defined, which is also connected in turn to the alignment and to all the other parameters of that model. So we have now created a workspace object called myModel, which is simply an assembly of all the model objects that we've now defined.